No, she's not.
Alright, guys, let's start. So we're looking at the nature of the reactions, right? 1.2.9, bottom of page 19. The reactions of electrovalent compounds in aqueous solutions are those in their hydrated ions. Remember that when an electrovalent compound goes into an aqueous solution, it breaks down into its ions, right? Because the chemical bonds do not have to be broken initially, example, all ionic chlorides react with silver salts in aqueous solution to precipitate into silver chloride. So we've got Ag plus and Cl minus, and will give us the compound or the precipitate of silver chloride. Right? Let's turn over. Okay, sorry, you were saying 1 second. Just note, most covalent compounds, particularly organic ones, right, react at a much slower rate since chemical compounds must be broken into addition to new ones being formed. Right?
Important thing to know is, by the way.
No, that's by the way. Right, so we're looking at this whole electronegativity thing. I gave you all the two periodic tables, and then now you can see in your periodic table, we can see the electronegativity there, right? So, what is electronegativity? Yeah. Right, this definition, you need to take it down your notes, right? Electronegativity.
I mean, you said electronegativity increases to the right, eh? Going up.
Yeah, you can see here. You can see it.
Yeah.
I think it goes this way.
Up.
Right. Yeah, it goes this way. It goes that way.
So what if you have manganese and chromium?
Manganese.
Chromium on the periodic table.
So manganese, what's the... Where were you?
I'm just looking at the periodic table.
Yeah.
Yeah, so we said it goes across the sphere, right? Manganese is 1.5, chromium is 1.6.
So this is a transition. Let's say we go for... Let's say we go here.
1.2, those are all perfect. All works accordingly, but I just looked at, oh, this one here is 1.6.
It's not only that one.
A few others.
Yeah, no, but it's fine because it's given, so you don't need to know which one is a high electronegativity. You work it out there, right? And you'll see which one, right? So we don't put anything there. Yeah. Yeah. Yeah.
They're all playing musical chairs, they all move around the spaces. University, university, you know?
Yeah.
Yeah, okay, I know. Take the first one. Right, electronegativity is a measure of power of an atom to attract electrons. Alright? Measure of power of an atom to attract electrons. Right? It involves the two terms ionization energy, right, and electron affinity. Right? Go back to the definitions of ionization energy and electron affinity. Maybe Sama, you can read first. ionization energy.
Is the energy required to remove an electron from a neutral atom or an ion?
Can I read loud? It's an energy.
Is the energy required to remove an electron from a neutral atom or an ion?
Right, remember that, guys? Ionization energy. Ionization energy is basically getting a compound into its ions, right? And then read the next one for us. Electron affinity.
Is the energy released when an electron
One
is
electron, yeah. One electron, yeah.
when an electron is added to a neutral atom or an ions?
Right. So that's what we're looking at. Ionization energy, getting a compound into its ions, and electron affinity, adding an electron to ions or a compound, right? Mulliken has defined electronegativity as the arithmetical mean of the first ionization energy and the electron affinity of an atom, right? Pauling's definition was somewhat different, and its electronegativity values that are given in the table. So this here is giving you the background now, the history of how we came around the electron negativity table. Fluorine is the most electronegative element. Just remember that that's comes out in the multiple choice.
Fluorine.
Yeah.
Good fluorine.
So I just want to show you the 2012 last year's paper, guys.
Why don't we helium?
Huh?
No, man, look at the
He was. So we're talking
Oh,
about.
in this table.
Yeah.
Okay, nice.
Right, guys.
Fluorine is the most?
electronegative.
So,
It's written, yeah. Right. So guys, this is your 20. This is last year's paper, right? As you can see here, question 1, right, is chemical bonding. You can see they tell you to chemical bonding. And then 1.1 is a true to 1.5 was a true and false question. Right, so it's a true, that's where you score some, yeah, 50% chance of
Hey, we ask me all
What to give a multiple choice?
our luck.
Right. So the next one, they'll provide you with some elements and compounds, right? The paper is always set up like this, by the way.
First section, chemicals, the
Yeah.
first chapter.
Yeah.
Okay.
So then they give you a list of compounds and elements, and then you need to match it. The question 1.2. You got 1.2 to 1.7, it's matching. So the first one, true and false. Second one, matching. So for true and false and matching, you're getting 7 plus 5, 12% for that day. Okay? And then question 1.3, they say, explain the statement by discussing the bonding that occurs in a hydrogen and chlorine atoms when they become HCl. So basically, you just have to write out the equation there. You start out by writing out the equation, and you explain what type of bonding occurs between HCl. What type of bond? Is it a covalent? So that's the thing. You need to know
Hydrogen and chlorine are both.
what. What is hydrogen?
Yes.
What is chlorine?
Chlorine.
Yeah. So what type of bond?
Iron.
Ionic bond. And then you're gonna state that there's an ionic bond between them, and then you have to give your definition of what an ionic bond is. What is an ionic bond?
Iron bond is when they exchange of electrons.
Yeah, you remember we said the keyword is
Ions.
keyword. What's the keyword for ionic bonding? Electrovalent bonding.
Transfer.
Transfer.
Electrons.
Transfer of electrons. So then there's another 3 marks, 15% there, right? And then the next one they ask you, okay, explain dative covalent bonding. It's in the second chapter. Give an example of dative covalent bonding. Also the second chapter. And then, on the dative covalent bonding, I think we didn't do it in this chapter, this next part. Yeah. And then in chemical geometry, it's 21 marks there. Question 2, they'll say chemical geometry. And they can ask you questions on that. I can't ask you anything yet because we didn't do it. But yeah, so it's question 1, bonding. Question 2, chemical geometry. Then question 3 is acids and bases. Very small section, very easy section to score marks here. Right, very easy to score marks here. And then last question, the descriptive chemistry. It's not hard. It's just that the last chapter of this textbook is quite lengthy. And there's properties of, I think there's about 7 elements that they go in detail to. You need to know the properties, the production, the uses. You know that? Sorry. Yes, but in
ammonia,
detail. Yeah.
All those things.
Yeah, so in detail. So in this one here, they'll choose one here. They say descriptive chemistry, and they chose hydrogen here. They usually choose hydrogen, oxygen, or nitrogen. So that's the common ones. Hydrogen, oxygen, or nitrogen. And then they ask you questions on it. They say like, part of chemistry of hydrogen can be explained in terms of its tendency to acquire the electronic configuration of a noble gas helium. And then they say discuss. And then they're asking you to do a reaction with hydrogen and sulfur and give the outputs. But all this here is in the notes in the textbook. And then we got descriptive, they got descriptive chemistry of all actually. So they got carbon, nitrogen, and oxygen, like I said. Yeah, carbon, also in carbon. And then you just have to give properties and the equations. All of the equations that you're gonna be asked here, it's in the notes. And all of these equations, all you do, you have to like learn it. You have to learn it. I'll give it to you. There'll be like some processes that you look at, like maybe the Oswald process or the industrial process to make, in a Haber process or industrial process to manufacture ammonia, nitric acid, all metric inorganic chemistry. Just lots of theory though. So for me, right, this, I would say always try and learn for exams. Try and push chapter 1 and 3 as much as possible. And then even if you score like 50% in chapter 2, it's fine. You'll get your pass over. Yeah.
Okay, so for the first chapter now, for your test as well,
Yeah.
we just work through past your papers, do question 1, and we should be fine.
For the test, I'm going to do revision for the test. So if you can answer my revision test questions, then you will be okay. Yeah, you don't have to learn from past your papers for my test. Yeah. It's coming from past your papers.
Oh, you already pulled it out.
Yeah, already pulled it out. Right, so yeah, now we're looking at how this electronegativity came on the periodic table and the reason for it, right? We know, we said that it will tell us about the ionization energy and the electron affinity, right? And there are different scientists looking at the definitions, different definitions, but this is the general definition, right? They say that fluorine is the most electronegative element, is given an arbitrary value of 4.0, right? And the electronegativities of atoms other than elements are related to it. And they've got a table there, and they're showing us all the different types of electronegativities. This was called the Pauling electronegativity values and some elements. The table shows the electronegativity decreases down a particular group. So if we look at the group 1 there, turn back to your periodic table, let's go to group 1. Right, group 1, we're starting there with hydrogen. Going down, what is the electronegativity of hydrogen?
2.1.
Alright, and let's go to next one, lithium.
1.
And the third one? Okay, we can see it's decreasing within the group. Let's go to group 2. The first one, beryllium, magnesium, calcium.
1.
Okay, let's go to group 3 with boron.
2.
Right. And aluminium.
1.5.
Right, the one below that? Alright, now let's see what happens, what they're telling us here. What happened there? It didn't work the way we said it wouldn't work, right? So they said the electronegativity, right? It decreases down a particular group. So it doesn't tell us all the groups, particular groups. So it worked for group 1 and group 2 and group 3 so far. But for group 4, no, sorry, it didn't work for group 3. Let's look for group 4.
Yes.
No, but it's all equal, so it's not decreasing. Okay, let's look at group, the next group, group 5.
Yeah, degree.
But then there's 1.9 and 1.9. And then group 7.
But group 2 also got 1 and 1.
What is
And
group?
0.9.
Oh, yeah, you're right. Okay.
Even the
okay.
first group.
It's also got 0.7, 0.7. Alright, next one. Let's go to group 6.
They all going down.
Seven.
All pins in.
Okay, 1.9.
Alright, and group 7, the halogens.
Yes.
And group 8. Group 8, does it have any electronegativity?
No.
Why?
Oh, it's in that.
Because these are
Ideal gases.
ideal gases, right?
They
They
don't
don't
react.
carry a charge. Yeah, they're noble, so they're like
So it's
perfect in
zero.
octet. There's no electronegativity on them, right?
So
So,
it's just at 1.
sorry?
Just that in group 6 that one that.
It didn't actually work.
Oh,
Yeah.
3,
Yeah.
sorry. Yeah.
In group 3, it didn't work perfect. Yeah. So they say that this is because an atom becomes progressively larger and the inner electron shells decrease the attraction between the positive nucleus and peripheral electrons. So when we're going to be looking later on in chapter 2, we're going to be looking at two things here. We're going to be looking at atomic radii, right? And ionic, ion. Yeah. So for an example, we got this is an atomic where the charge is 0, and this is like, for example, this is an ion radii or ionic. And then in terms of this here, what we're talking about, if we let's say for example we look at aluminium, what aluminium is? How many?
3.
Group 3. See how many? 13. Alright, so 13 electrons here, right? So we got number of electrons equals 13. What's the charge on aluminium? Is neutral. Sorry?
Oh, you mean
What's the other periodic table? Sorry, 1.5.
1.5. And yeah, so what group is it?
group 3?
Group 3.
Yeah.
So the valence electrons will be equal to
Plus 3.
3. Plus 3. 3. And they go.
what we saying here? It's in group
3.
3. Yeah, so it will be
3.
Three.
Valence.
from group 4 onwards.
Oh, okay.
Minus subtract.
Blah, stop that.
What I do? Wasn't it? Blah.
Right. So this is what we. So in terms of this part we're looking at next year, right? Atomic radii and ionic radii. We're looking at basically. Check what period it is in. Period.
3.
1, 2, 3. Yeah.
Period 3 equals 3 shells, right? So let's say we have our nucleus here. So around the nucleus we have 1, 2, and then 3. Right? And within this here, we're going to have our cloud. So, but what we're looking at is atomic radii is the radius of the atom. So when we're looking from the center of the atom to here, right? So this is our radius. Right now, what they're saying is, right, as we move, so electron negativity increases in a particular period in alkali, right? What are we talking about? This is because the atoms, yeah, there's a gel. This is because the atom becomes progressively larger and the inner electron shells decrease and the attraction between the positive nucleus and peripheral electrons. Remember, we are looking at the examples here on the screen, and we're saying, so if we're looking at this and this, which one will have the larger radii?
It would be
Which one? This one will have a larger radii, or this one?
This
One and
one.
two.
I'll turn on the top
This
of
one.
the eye.
Bigger plus 2.
plus 2.
And then,
So this is an
Lost
ionic
two
radii
electrons.
because it's in ion form. So that's why it's called an ionic radii.
Aluminum.
This is atomic radii because we're just looking at the elements.
The one on the right hand will have a higher radius.
No, we're looking at the larger radius.
So
Yeah.
So
This
you're
one.
saying this one here.
No,
I said
this
that
side.
one.
It's given off.
It's given
electrons.
off.
It's given off electrons.
Yeah. So what will happen is here
Electrons.
we got total electrons here is number of for this one is 13.
Yeah.
But for this one here it's gonna be 13 minus 2.
Minus.
Yeah. Is 11. Right?
So on the
11 would be
So this one here, because it has 11, it will now probably have, and it has more protons, so the pull of the
To the
cloud
center.
to the center is greater. So the radius will be smaller. So this will have a larger radius. Right?
makes sense.
Yeah? Okay.
And
Right,
if it
so
was positive, I mean, if it was negative,
then the opposite.
Opposite.
The opposite is true. Yeah.
Bigger.
Yeah. Right, so a bond formed between the two atoms of similar electronegativity will be essentially covalent. Right? And usually when it's similar electronegativity, right, and if it's a covalent bond, it's usually going to be between a what? Two? We had in the board?
Covalent groups.
Two?
Non-metals.
Right.
Yeah.
It's going to be two non-metals that's going to combine with similar electronegativities, right? Yeah. Let's go to the next page on the top. The further increase in electronegativity will result in an increased polarity, right, of the bond, until eventually the electron pair can be considered to reside almost entirely on one atom, right? That is an electrovalent bond will be established, right? Electrovalent bond is your ionic bonds, right? So that means something that is positive and negative coming together. And it is showing us that there a covalent bond between A and X and a polarized covalent bond is when you have a positive pole and a negative pole, right? And then we have an electrovalent bond. It's just between remember, it's between the negative and a positive. So we're getting this looking at the three types of bonds there, right? Electronegativities of the atoms increase in order. So we're looking at X will be less than Y, will be less than Z, right? It becomes clear why group 1 and group 2 elements react with group 6B and 7B elements to give essential electrovalent compounds. Calcium chloride, and you got the CS plus F minus, being the most ionic compound. On the other hand, so let's look at CS. Find the charge for CS, find the charge for fluorine. Find the charge for CS. And what's the charge for CS?
0.7.
Right? And for F?
4.
Right? So you can see these are on two ends of the spectrum. Meaning, yeah. So it becomes the most ionic compound that we can get, right? You can just write that, highlight that there. CS plus and F minus, because this here comes out in a multiple choice thing.
F minus.
So they'll ask you in the multiple choice, which of the following is the most ionic compound? And they'll give you like different ionic compounds, and then you'll have to work it out. How you work it out, which one is the most ionic? One that is the extreme on the left and extreme on the right. So just say for example, we had HCl. Let's say we had HCl.
Right.
And we had, what's this other one here? We got CSF. And now let's look at the H and Cl. Give me the this thing here.
H is
2.1
Yeah.
and
2.1 and
3. 3, scale is 3.
3.
right. So 3 minus 2.1,
0.9.
right? And then let's look at this one here again.
CS is 0.7.
0.7
Yeah.
And F is 4.
plus 3.3.
Yeah. So they're saying that this year is, you shouldn't get higher than 3.3. So when you're working it out in a multiple choice, right?
Yeah.
This is what you're gonna do. They're gonna ask you this, right, in the exams. They're gonna say which one is the most ionic compound. They're gonna give you about 4 or 5 compounds there,
Yeah.
and then you're gonna use this here. You minus it, work out the difference between the electronegativities. The one with the highest electronegativity will be the most ionic. You got it?
So CS.
Yeah.
C,
But
C
take down this example, the CS, because this one here is a common. It's common to come out. You're okay.
Yes.
which is most ionic.
Yeah.
So obviously the one with the greater difference is higher.
Yes, the higher, yeah. Right, now let's go to the next paragraph. The reason why aluminum fluoride is an electrovalent compound, right? So aluminum, where does aluminum fall? Is it a positive or is it a metal, non-metal? Yeah.
that's
It's a false as a metal.
Or it falls as a metal. And where's fluorine?
Fluorine is a non-metal.
Right. So they say the reason why aluminum fluoride is an electrovalent compound, whereas aluminum chloride is a covalent. So where's aluminum again now? You got aluminum, right? It's in the same thing, and then your chlorine is in group 7. Right. So, but why is aluminum fluoride an ionic compound, while aluminum chloride a covalent compound? And then they give you the reason is because fluorine atom is the most electronegative, is more electronegative than the chlorine atom.
This is means you have aluminium chloride and aluminium fluoride.
Yeah.
The question is,
So they say, so this is like something that you have to learn, right? It's like a trick question, right?
okay.
So you got aluminium, which is a metal.
Mhm.
You got everything in group 7 is your halogens, it's all negative, we know that, right? So obviously, usually we have, when a non-metal and metal combine together, it's usually a transfer of electrons, right? And when we have a transfer of electrons, it's a what bond? Ionic bond, right? So they tell us that aluminum fluoride is an ionic bond, but they say, hey, aluminum chloride is not an ionic bond. It is a covalent bond. And then they tell us the reason, because the fluorine atom is more electronegative than the chlorine atom, right?
Are these exceptions to the rule?
Yeah, this is an exception to the rule. Sorry, guys, exception. No, I told you.
Okay, so there's no.
As I've said, no, the reason why.
So then it flows again.
Why it tripped us before?
no.
Oh.
The other day.
Alright, so There are some exceptions to the rule that you have to learn, right? So for that one there, guys, just also highlight it. It might come out.
Aluminum chloride?
An explanation in terms of the lattice energy would run as follows. Since the fluoride ion is smaller than the chloride ion, the lattice energy of the aluminum fluoride crystal structure would be greater than the similar aluminum chloride structure by virtue of the closer approach of oppositely charged ions. In instance, the two explanations amount to practically the same thing, since the fluorine atom is more electronegative than the chlorine, the atom, because it is smaller and consequently gives rise to smaller anions. Nonmetals that form negative ions or anions do so by gaining sufficient electrons from metals atoms to attain the electronic configuration of a noble gas. Right? The following are few of these structures, and they show us the neon, the argon, krypton, and xenon structures. Many simple cations also have noble gas structures, right? Example, those formed by the metal groups of 1A and 2A. There are, however, many cations whose electronic structures are in no way related to those of noble gases. The following three classes are apparent. So we're going to look at the three classes, which are firstly cations. And remember, we spoke about what a cation is. Right? It's an ion that is positively charged. Cat, it's your pet, positive.
That's a better one.
Huh?
That's a better one.
Yeah. So that's what I said.
The onions of
It's
the.
an onion is sad.
Onions makes it
Onions makes
positive because you're happy.
Yeah, you cut the onion, you start crying. Right. Right, 1.3.1, cations have 18 electrons in their outer shell. Examples of cations assuming configuration are one valent ion of copper and silver, and two valent ions of zinc, palladium, and mercury. Turn over, guys. We're looking at table 1.2. Right, table 1.2 shows the electronic configurations of the atoms and ions are shown, right? So we got copper, and we got the atoms and its ions. Now you can see there it's got 2.8.18.1, and we got zinc. It's 2.8.18.2, and you got zinc 2 plus. 2.8.18. You can see the charge, when you have the charge there, it's just minusing from the number of total electrons. Alright? This is a condensed formula of the electronic configuration. Remember we spoke about condensed?
Yeah, but I'm trying to figure out how to cut right at it.
It's 22.
22 now.
Now I know, I'm saying that 8.1.
Yeah.
How do you get the top? This is
It's a condensed electronic configuration in the orbitals.
orbital, huh?
Right? S orbital we got 2,
Yeah.
P orbital got this thing.
Oh yeah, yeah.
Eight.
Everything up will come to the atomic
And the next
number.
orbital got 18.
Okay, cool.
Yeah.
One of them.
And then what you can see there, remember I was showing you on the board here, it's the same thing, right? It's the same thing. I was showing you guys that when you have the copper, right, and then look at the copper plus, what happens to the one electron? You can see it disappears. Yeah. So what it will tell us that in terms of the radii there, when we're looking at the next chapter, the other one will be bigger. And we're looking at zinc and zinc 2 plus. You can see the 2 plus will take away 2 electrons. And so on, you look at the silver, cadmium, and mercury, same story, right? And then this is examples of cations having 18 electrons on the outer shell, right? Cations of 18 electrons on the outer shell. So in the last shell, got 18 electrons, right? Then we got cations having 2 electrons on the outer shell, and those are thallium, lead, and bismuth. The same explanation there, right? And they're showing us the breakdown of its electronic configuration. And then we're looking at cations of transition and inner transition metals. Now that's in between here. So we're looking at the periodic table.
Yeah. The part that's
Yeah.
down.
Yeah, those are transitions.
Yeah, so we're looking at the periodic table here. We're looking at this one here in between.
From here to here.
From here to here.
Sorry, before you go there, what's the difference between the anion, the
So they're just showing us the different phases of the
all is
cations.
the same?
No, the outer shells of the last. Can you see the outer
Yeah,
shell?
so you lost one.
No. This is a cation, right? On this side.
Yeah.
This is an atom of the ion. So they're showing us the cations that have 18
Yeah.
electrons in the outer shell. It's these ones. And then they're showing us an example of cations having 2 electrons.
But the first one's got one.
Sorry?
Got one. Ti.
No, in the outer shell. You can see the outer shell got 2. The last shell.
Yeah.
Outer shell means the last
the
shell.
last shell. Okay, right.
Outer shell means the last shell. It's recording. Yeah, so basically they're just giving us the rundown about cations and they're showing us the different cations with different outer shells. They started off the metals with 18, then we went to the ones with 2, and now we're looking at cations in the transition metals with a specific one. In transition metals, the metals can act in almost 4 forms. It can be 4 different types of cations. It can be, let's say for example, right, cation transitions and inner transition metals. For transition metals, cations have from 9 to 17 electrons in the outer shell. Right? Examples include, right, we've got V2 plus, Cr2 plus, and Fe2 plus. And they got V3 plus, Cr3 plus, Fe3 plus. And you can see there, in the outer shell there, we got 11, 12, 14, 10, 11, 12, 13. Right? None of the cations falling into the above 3 categories is stable, as one will a noble gas configuration. This can be seen by comparing the successive ionization energies in kilojoules per mole of an atom forms a noble gas like iron. Example, aluminium with those of say a transition metals, example, vanadium. And then we're looking at aluminium here, and we're looking at 4 forms of aluminium here, right? The first one there, Al, right? It's not a cation, right? Al there is not a cation. So we're looking at like Al like this here. This is not an ion. This is an atom, right? Then we got aluminium acting in Al plus, right? And the outer shell, how many electrons?
2.
Right? Then Al with 2 plus, outer shell,
One.
and then Al has 3 plus outer shell,
Nothing.
8.
and then Al